Hello, everyone. I'm Rijnard. Here in my talk about Parser Parser Combinators for program transformation. So a little bit about me first. I recently defended my PhD at CMU, where I worked on topics in program transformation, program analysis, and program repair, and especially on automating these techniques so that we can have things like automatic bug fixing and large-scale refactoring in new ways. I'm heading off to industry next, where I'm going to work at a startup called SourceGraph. And here I'm lucky because I get to work on these same ideas and develop them in a way that integrates with developer workflows that you might all be familiar with, like code search, code intelligence and navigation, and code review. I love developer tools, and my favorite color is OCaml. So that's me. Let's talk about you and what this talk has in mind for you. So as you're probably familiar, code changes. Code changes all the time. So the Greek philosopher Heraclitus had these ideas that change is the only constant. I'm pretty sure that he was talking about code change. He just didn't know it. So I'm going to jump right into a demo to kind of demonstrate what kind of code changes do we perform to make code more readable, the kinds of refactorings that you probably do every now and then after implementing some new feature. So I'm going to look at an example in Go first. And so this is a static check tool that does all kinds of linting type checks or static checks. I'm not affiliated with this tool in any way. I just like looking at tools that give kind of idiomatic patterns for expressing changes for all kinds of languages. So here, it turns out in Go, you can simplify some error constructions. Specifically, if you're constructing an error where, oops, that skipped. There we go. When you're constructing an error, you might write out some formatted string, and you can actually use a dedicated function called errorf to do that instead. So this is documentation for a tool that does a lot of things in the underlying representation, so in the abstract syntax tree. And I'm going to show you how you can turn documentation like this into an actionable code transformation that you just run in your code, and to do that declaratively. So Combi is a tool that I wrote to do this sort of transformation. So with Combi, you specify kind of declaratively what you want to see in the transformation. So in this first argument on the command line, we're just going to write out this before pattern, and everything is going to be concretely the same as what you see in that documentation, except for the arguments of this sprintf call, which is going to be bound to some variable, some alphanumeric variable name. Here I'm just using the number 1 enclosed by some square brackets and a colon to denote that this is a variable or a whole that can match this syntax. So in the second argument, we write out this after pattern that we're interested in, and we refer to that variable that we've bound to some syntax. And we're going to specify that we want to run this on all Go files in the current directory. So running this pattern, we find one instance in this source code where we can rename this function and extract out the argument of sprintf and put it in this errorf call. So this is actually an example that I ran yesterday on the Go compiler source code. And so if you want a freebie to go and contribute something to the Go compiler, here you go. I have not opened a pull request. This has a good chance of getting accepted. It is also the only pattern that I found in the code base that exhibits this. All right, so to just demonstrate that, well, that's a preview, and we can actually just perform the change in place by adding an in-place specifier, and then in your diff, you're going to see something like this that you can PR. All right, so wouldn't it be nice if we had something like this for any language? And I do mean any language here, right? So the ability to kind of, in a structured way, match and rewrite syntax without caring too much about the underlying implementation. So what I'd like you to take away from this talk is a new way to change code, both tooling and thinking about ways of changing code in a structured way. So the way I'm going to structure this talk is first kind of give you a deeper understanding of program syntax, manipulation, and challenges in these areas in terms of tooling and scaling this idea or generalizing it across multiple languages. I'm then going to talk about my solution for manipulating syntax and give you some exposure to some neat ideas in a functional paradigm that allows this mechanism to work. And throughout, I'm going to show you some practical tooling and demos to show you kind of the contextual information and examples that make it relevant to activities that you are probably engaged in. So being an academic, I'm going to talk about some papers. I'm not going to dive into it deeply, but this is an interesting paper from 1992 on language design for program manipulation. The point of this paper is just asking the question, well, what are sensible choices for program syntax and to some extent semantics if the number one concern, if the thing that we cared most about was the ability to change this program easily? So there's this closing sentence in this abstract, design principles are suggested so that problems identified for current languages can be avoided in the future. They were not avoided. To give you one example of these principles, here's some concrete syntax on the left, 2 examples of some if condition in the body that parse to the same underlying abstract syntax tree in languages like C and Java. The one has braces, the other does not. So we have multiple concrete syntaxes that refer to the same underlying data structure. And so there's this principle that, well, the concrete syntax diverges from the abstract syntax tree. And so that's not a desirable property if we care about changing code. What that means practically is, there's more work for analysis tools, compilers, and so on, converting to this representation and giving it back. If you only had the AST here, which concrete syntax do you map back to? I'm not saying that we should not have ambiguous or different concrete syntax. I'm only pointing out that the choices that we make in languages that are convenient sometimes or more readable have implications and consequences in the underlying tools. And so this can crop up just for one language. What about multiple languages? Humans are very creative, and we are no less creative about writing out and designing programming languages. We are very inventive at using different names, different syntaxes to express similar ideas in different languages. And while I know you're probably only working in one language at a time, but wouldn't it be nice if we had a consistent experience, an ability to rename or manipulate syntax across all of the languages that we use day to day? And part of this complexity introduces problems for tooling. Maybe you use a language that's very popular and you have a very rich tool chain to choose from, but maybe no one wrote a tool yet for the language that you're interested in. So one of the languages that I've recently started playing with a lot is Elm. And Elm has a lot of really great tools, but there's some changes that I want to make sometimes to my program that can be automated. And so I'm going to show you one demo here in Elm using my tool where you can simplify this left-hand pattern here to the right-hand one. So you can map, for example, the same function across the same function where you would otherwise do this at multiple layers on the left-hand side here. And I'm going to show you a demo in a live environment. So this is available online at combi.live. And I'm going to kind of walk you through how you can develop patterns like these and then apply them directly to source code. So first, we're going to look at how to match things that we're interested in. So in this case, what we're interested in is this list.map pattern and then things after it. In the default case, we might have a hole like this expressing everything after it. So this includes new lines, for example. But right now, we're actually interested in just the first argument or function here. And for that, there's a slightly different syntax to match identifiers or alphanumeric characters using these double brackets. So if we change this pattern a little bit more, and extend it to match this piping operation, you can see, okay, we have consecutive piping for this list.map, and we've matched both of these arguments that we're interested in, and now we can rewrite it to this other form that's a little bit shorter and which I personally prefer, where you can use just one list.map operation and then chain these functions using this function composition operator. All right, so again, this is now a capability that you have in Elm or a different language which might not already have a linting check or a refactoring tool. Other times, maybe your language of preference is getting extended, so you have something like Python, right? Apparently, they might get assignment expressions soon. And so what if you needed a tool that can refactor that, but that's not yet integrated into some Python toolchain? And if you're very fortunate, you might have powerful tools like Clang, that works on your C program, but all of a sudden when you introduce inline assembly, you're out of luck, right? Like this doesn't parse anymore. So this is why we can't have nice things. People have to implement tools. People have to take into consideration syntax extensions, changes in representation, and changes in whether you use other features like macros, inline assembly, and so on. So let me tell you about nice things, right? So another way to perform lightweight syntactic transformation and tooling using the approach that I'm talking about today. So to take another example, we can remove redundant nil checks in Go in this code fragment. So this is, again, another kind of syntactic change that you can perform when you are ranging over this variable. You need not necessarily check whether it's nil if it's a slice or a map. So from this documentation, we can actually just remove that surrounding if check to produce this just the for loop on its own. And what I want you to take away here is that here's the implementation for this check, right? I'm not expecting you to actually read this. And I'm sure if we all had time, we could implement a check like this ourselves. But you have to become familiar with the underlying AST, learn this visitor API, and implement it in your language of choice. And this is a lot of effort if you're interested in doing the same for Rust, C, Haskell, or your language of choice. So again, I'm proposing a solution here that's syntactically close to the code that you want to change. And when I got feedback on making these slides originally, the part on the bottom here is the proposed solution, and people told me, well, I don't really see the difference between the example you're giving and the actual change, and that's the point, right? So we want something closer to syntax, but that can match structurally on things like nested constructs that regular expressions are not powerful enough to do. So I'm going to walk you through an example of writing out a template that performs this change and kind of the properties of doing that. So here I've copied some code again, just this fragment where we're going to match on this case. So in the first part, we write out this if condition and then match on some expression, which I'm just going to bind to this variable expr. And then we can add these braces. So the thing about Combi is it understands that braces, parentheses, brackets, these are delimited by default. So if you enter a hole between these, it knows that they should be balanced. This is not like regex where you're matching sequences of characters and hoping to match a balanced delimiter. So it understands that by default. Now we can expand this pattern to then include the part about the for loop. Here I'm just calling x to bind to what's being assigned from the range. We don't really care about it. And then again, specify this expr part, which is the hole that refers to the part that's being checked against, right? So the fact that I'm using the same variable name here means that those two things must be equal in what they're binding. So we see this test.flags being the same thing that's checked against as the part in the for loop. All right, so we've matched the parts that we're interested in against this source code, and now we can rewrite it. So I just copy this template, paste it on the right-hand side here, and now we can rewrite it by simply removing that part of the code. So that's the demo. You can follow, you can go through this yourself. Again, at the bottom right there, there's a link that has the example written out for you. So this approach is syntax only. I am not introducing any knowledge about type information or variable scoping. And that's as a first pass for enabling a very declarative way of just manipulating syntax. And because it's syntax only, nothing about this really is Go specific. So the check, of course, is Go specific, but what I mean is syntactically, there's nothing Go specific going on here. For example, in Dart, you might want to perform this change where instead of checking a list against whether the length is 0, you can use a built-in dedicated attribute to check whether it's not empty. And that's actually more performant compared to a linear, a check that's linear of the size of the list in the former part. In Clojure, there are more idiomatic ways to check things against nil. And in Scala, you might be able to simplify a chain of function calls into something simpler. And so all of these languages support this notion of balanced delimiters and expressions inside of them that we are interested in renaming. And this is relevant because, in general, we can't use regular expressions to do this sort of thing. Who is familiar with this post on Stack Overflow? A lot of you, okay, good. If you're not, do check out this URL or just search like Stack Overflow regex HTML parse, right? Regular expressions are not good at parsing structured languages, especially nested languages. And I love how this ends because it's just like, have you tried using an XML parser instead? We use parsers to parse languages, not regular expressions. So in order for an approach like this to work and to actually apply to multiple languages, we need a parser for multiple languages. So now I'm going to go into a little bit more technical detail about what underpins this approach and what allows it to work. So in this parser for multiple languages, I identified that there are shared context-free language properties. What are context-free language properties? Things like balanced delimiters, balanced parentheses, braces, and so on. This syntax fundamentally delineates trees, right? So blocks or blocks of if conditions and so on. And so a way to achieve building a parser for multiple languages is to say, well, at a high level, let's take something like a parentheses language. So a grammar that can generate phrases in this language that are always balanced with respect to parentheses and extend it in a way that models modern languages. So there's a bit of math involved here. If you're interested in the math, you can go check out a paper that was published at PLDI in June. I don't want to go too much more into the math, but the point is that we need a more principled way to deconstruct languages so that we don't run into this problem, right? So a simple grammar respecting this kind of structure, I'm showing up here. So all that this grammar is going to do for us is it's going to parse things that are balanced with respect to delimiters, and everything else is going to be treated as a token. So to give a practical example, let's take some Go code of hello world, and we can decompose this with respect to delimiters according to this grammar. So it looks like this. It includes white space. So this func main part in the beginning, that's one token. According to this grammar, the only things that we care about that's deconstructed are things between and inside delimiters. And that's what this grammar expresses. As a first pass, this is useful for identifying these kinds of patterns so that we can rewrite them at a structural level. Now, there's more details in the paper about how we deconstruct with respect to white space or punctuation and so on. But at a high level, that's the important part. So I told you how to represent code so that we can achieve transformations like these, but how do we actually match declarative templates to source code? So given some template, how do we achieve this ability to match and find things that we're interested in? So show of hands, how many people are familiar with parser combinators, have used libraries or read about them? Okay, great, I'm at the right conference. If you're not, this is your one-sentence summary of what a parser combinator is. So it's a parser modeled as a function that can be composed using other higher order functions to implement your grammar. So parser combinators are interesting because we can implement a function that serves as a parser for an int. So given some input, produces an int. A parser that, given some input, produces a string. We can combine these parser combinators and produce a parser that parses an expression. And parser combinators are very interesting because they're polymorphic in their production, meaning we can really write a parser for almost any type, including parsers. So we can write a parser for parsers. And really, that's the underlying mechanism that achieves this ability to match declarative templates to source code. So this template is actually something that defines a parser. Now, before I go into the next part, this is just the secret sauce, right? The underlying mechanism of what makes this approach work. You don't need to actually understand any of this or write a parser to use the tool. It's for your intellectual curiosity. So all of these languages are already supported at some level with respect to string syntax, comment syntax, and delimiters, right? So no need to worry too much about, how do I figure this thing out? How do I use? This is for your intellectual curiosity. So let's dig into this a little bit more. Given some input template, what happens underneath the hood is, well, as we parse this template, we see, oh, there's an if. If we parse an if, we produce a parser for an if. If we parse some white space, we produce a parser for some white space. Identify this whole, produce a parser that matches and stores text according to what that whole respects. So maybe alphanumeric characters, maybe everything up to this not equals nil. When we parse braces, they should be balanced, and we produce a parser for balanced braces and do that recursively. When we chain all of these parsers, now you have one single parser that expresses exactly what you're interested in matching here, and you can just run it on the source code. If that parser succeeds, you've matched something, and now you can rewrite. And so that's the underlying reason why I call this Parser Parser Combinators, because what you're doing is you have one parser combinator that produces other parsers to match the underlying syntax. And one interesting kind of side effect of this is that there is no definition of an AST here at the code level. There's only functions and parsers that define what you're interested in matching. So that's cool, but where's the complexity, right? So why doesn't this tool already exist? Why can't I just do this for a lot of languages already? So let's look at some code. But let's treat this textually. So those parentheses are balanced, ignoring the top part if we thought about comments. Okay, there are some balanced parentheses if we don't know what comments are. And if this isn't C code, well, in Python, this is a different syntax for comments. What does this mean? If we treat text as sequences of characters, we don't know anything about the knowledge of or distinction between code and data. An editor is going to highlight some of these things for you, and conceptually we think of things in this way. But if we're actually interested in matching things like arguments or comments or strings and using regular expressions, well, this is only going to end up with more problems, right? And if you do this for these complicated code examples with varying syntax, this is not just like turning 99 problems into 100, it's like order of magnitudes more. So to give you an example of how this pans out in the actual tooling, I'm going to show you a very quick demo where suppose we treated this fragment of JavaScript or TypeScript code as text, which Combi can also do. And we want it to match on, say, conditions following an if statement. So here we're matching everything inside possible comments, inside code, and inside data, or the string that you see below here. And what you can do is actually change the target language that you're interested in. So currently text was selected, and we can select something like JavaScript or TypeScript instead in this live debugging environment, which corresponds to some command line option that you can specify when you're running this on your code base. And then doing that change will help Combi recognize, OK, there's only one part here that actually refers to code. Now, if we actually cared about matching strings, what we can do is we can enclose a hole inside of string quotes. And because Combi understands kind of the structure and syntax for strings, it can identify the string contents here. And if we knew the contents of the string that we were interested in, maybe we'd want to match on something like if and ignore the parts around it. So this underscore is just ignoring parts before and after the string that we're interested in here. And so we can match on that same condition inside the string. So there's this distinction between code, data, and white space or comments. So to implement this complexity and support more than 20 languages in this way is really done with small parsers that handle these syntax idiosyncrasies across multiple languages. So here's the definition for Go. Basically, it only specifies that there are balanced delimiters. There's some syntax for strings, and some syntax for comments, and that's all you need. And that's also the extent of expressivity that's available to you for matching. And these small definitions embed into a larger parser skeleton that give you that engine for matching and rewriting code. So that's all of the tooling. I'm going to transition over to talking about applying some of these ideas in the real world and at scale. So as part of kind of validating the approach and applicability, I took the top 100 GitHub repositories for 12 languages. I wrote 1 to 3 of these rewrite rules or patterns that already exist in linters, checkers, or refactoring tools. And so I applied this to over 250 million lines of code, and that takes about 42 minutes on 20 cores. So the approach is quite fast. You can run this on quite large code bases just on your laptop. Of these changes, made pull requests to over 50 unique repositories, merged over 40 of them. If you want more examples of the patterns or the actual code that was merged, you can check out the URLs at the bottom. Just one example of such a change in the Rust compiler. So there were about, I think, 60 instances of redundant uses of referring to variables using a struct field. And so you can just remove that if they are the same name. All right, so as a final demo, before wrapping up the talk, I want to show you a little bit more advanced capabilities for refactorings that people have run into giving me feedback on the approach. So in this part, I was looking for examples where I could show something representative for rewrite rules that can nest. And so what I did was I looked at some popular Haskell programs, and I looked at the commits that used this and searched for commits that committed things with HLint or the Haskell linter. And what I found was that there was this interesting case where you can rename a concatenated list of strings and just use an infix operator to append these strings instead. So that's an example of a diff that I'm going to show you for rewriting. So I copied this over to the live environment, and the first part is just matching on this concatenation of strings. So we're interested in the body of this list that's being concatenated. And then in the rewrite part, well, we're not going to need this concat part. So the first part that here is to remove the concat. And we're no longer going to care about the list brackets in there, since we're going to use the infix operator to concat those strings. So now the question is, well, we have this list. We need to rename those commas to the infix operator. So how can we do that? Because there are multiple repetitions of these things inside the list. So Combi has a little bit more advanced usage where you can specify rules to do this. One of these rules is to rewrite in place the contents of this variable. And so it's quite simple. It's just a recursive application of this original pattern that we have. And what's going on is that we'll just map this comma to this infix operator ++. And so just to demonstrate, when we change this right-hand side of the rewrite, it changes in place for the code. All right, so again, we can copy that pattern and run it on the code base and then get a lot of output. Sometimes you want to run a formatter to re-indent the code, for example. There's also ways to manipulate the white space indentation in Combi. There's more examples of that if you are interested. Let me know after the talk. All right, so we have a lot of diffs, and we can actually apply this change to our code. So in summary, before I summarize the talk, if you're interested in the tooling, check out the GitHub, or let me know if you're interested in maybe running these patterns in an editor or in your CI. These are definitely things that I am in the process of exploring. So in summary, I told you about language design for program manipulation. Things that make this space hard, especially for support across multiple languages, just in terms of syntax and breaking down syntax in a way that makes it possible to recognize things that you're interested in changing. I presented a simple grammar that can deconstruct programs for most languages in a way that makes it amenable for matching. I then described how I layer on top of this a way to match programs declaratively using templates. And the way this is implemented underneath the hood is with parser combinators that are generated from parsers by parsing this input template. And that actually removes a lot of complexity because you can just define parsers for the different parts of syntax that make this whole process troublesome. I shared some of our results with applying this to large-scale programs and online. And then I gave you a lot of demos that hopefully gave you a taste of how the approach works so that you could use it yourself. I'm happy to take any questions, and thank you for your time. Yes. So the question. So the question was, have I thought about using this for code highlighting? Because those approaches tend to use regular expression patterns to highlight code. The answer is yes, I've thought about it. No, I have not actually implemented anything for it. I believe A, it would be fast enough, and B, it would be more useful. There's definitely some code that you could view on GitHub that breaks, and you can see that manifest. And I think this would definitely be able to handle that complexity and also do it efficiently enough. So definitely something worth exploring. Yes?
Where do you want to take this next? Like, my first thought is, this would be so great to have this the list of rules that you want to run against this class. Like, what's your vision?
I think as a priority, large-scale refactoring is where I think the real benefit lies. The ability to completely stomp out, right, certain code patterns that are just known to be bad or buggy and can be rewritten in different ways. Wouldn't that be like great, right? There's so many opportunities I realized doing this work for just making code better in a very consistent way. So I think large-scale code modification is where the largest kind of benefit is. At an individual level, I really see this also integrating with editors, right? So there's a place here where it's great in the CI pipeline, but I think a lot of this stuff can be preventative and not so much reactive. And so I'm also focusing on, well, A, it's efficient enough to run in your editor, right? So there's really stuff that we're targeting where it's like, under 100 millisecond, 200 millisecond runtime, and you have a catalog of changes that maybe you care about. And so I think there's a lot of opportunity there at an individual level. Yes? Yeah, so the question was, are there cases where transformations would change the code and it wouldn't compile or it wouldn't be correct? So this is a really interesting question, and kind of I'm doing follow-up research in this area because it's great to have a very powerful way to change code, but that obviously means that you have more opportunity to mess things up. I'll give you a good concrete example. So that if nil check that I showed you for Go code, well, that only applies to maps and slices. It turns out in Go, you can also do the same kind of pattern on pointers, but you wouldn't be able to rewrite that code if it was a pointer. So what additional information do I need? I need to know type information, for example. So there are many examples, actually, where you can transfer code only if you know the type. And you can't tell what the type is just by looking at the syntax. So I already have ideas on extending this to also incorporate type information to say, OK, perform this transformation if I know the thing that was matched here is of type int or string or pointer. And that would incorporate into the rules framework. So that's one concrete example. Malformed syntax, that can also happen, right? But there's less possibility of generating malformed syntax because you can't match on, for example, unbalanced parentheses or expressions. So there's some built-in control there that gives you more confidence about what you're matching at a syntactic level. Do you have a follow-up question? We have time. Yes. Depends what you mean by a library. It's available as a command line tool. If you want bindings, I believe there are Python bindings that we have in the works. I'm not sure exactly what other form you would want. C bindings might be something that can be supported. Feel free to open a GitHub issue. It is implemented in OCaml, yes.
Have you ever considered transpiling, using this to transpile software from language A to language B?
Definitely a use case that I've been interested in and thinking of. One concrete example is CoffeeScript. And I think that last example that I showed where you want to also transform things, say, inside a list, so separators and that sort of thing, you really need that kind of capability to do a richer set of transpiling. I have not tried to apply it in a large use case scenario, but I believe there's a lot here that could be done to make that successful. Thank you.
What's my
So the good news is it's always going to parse, right? Now, if your macros, for example, contain unbalanced parentheses, you can kind of inform the parser that, oh, just ignore macros for now, right? So you could treat macros as a comment, and then it's just going to be ignored. Now, if you're interested in actually changing macros and not the rest of the program, just use a different parser or language that understands, okay, macros can be unbalanced or whatnot. Identify those parts of the code. In fact, there's some interesting research at CMU where we have one professor that does a lot of work in macros. And so one interesting thing is that it's actually bad to have macros that aren't balanced in some sense. And so you could use this approach to actually identify macros that are unbalanced as well. There's a trade-off here where you can basically use the parser to identify the parts of the program that you're interested in. Okay, let's go from the front to the back. Yes?
Do you consider using it for symbolic transformations, such as symbolic algebra, where you have repeated transformation of like a formula that you shrink or you want to apply for some normalization?
So the question was, is there an application possibility here for symbolic formulas, for example? Yeah, so take something like SMT or SAT solvers. If that was maybe one form of syntax that you'd be interested in, yeah, write, for example, normalization routines to simplify various parts of this tree. That sort of possibility exists, right? So one idea that I've also had is to take input and from source code and just convert it, for example, directly to something like data log as a declarative method of translation. Let's go.
Speaking of Combi script, is there a way that if I wanted to match on a colon followed by a square bracket literally within like Combi script? Or would that
Yeah, you would write a colon followed by square brackets. Between? Oh, the colon. So the colon's square bracket syntax. So it's a good question. So the question is, okay, can I escape the syntax that I'm using here, the meta syntax that is binding variables? So in practice, what's interesting is that we haven't found any conflicts in practice with code using that syntax. Now, there are ways to escape it, but the thing to point out here is that actually it's only valid in this case when there are alphanumeric characters inside, right? That's the only time Combi is going to recognize it as a variable. If there's anything else, if it's empty, if it has an expression, then it's not considered a variable. So I think your CoffeeScript use case wouldn't run into this issue. Got it. Okay. That may be a case where you'd need to escape it. Thank you.
What are the capabilities for combining multiple parsers? Like if I were to build out, for example, like transforming a language, you can combine 100 parsers potentially and have transformation. What would a format for that look like?
So the question was how to combine kind of these templates into one maybe pipeline that you'd run after each other. So there's a couple of options here. The way you would do this in practice, right, is one input format for this is you create a directory for each transformation you're interested in, create subdirectories that say, okay, this is the match, this is the rewrite. And you can specify this, and Combi will take that directory and recursively look at all the directories with their match rewrite patterns, and then apply all of them in that sequence that the directory structure is in. So sometimes you want an ordered sequence, and so you can also use the directory as an alphabetic sorting method to sequence those rewrites. So there's more of that in the documentation on the website. So that's how you would do it in practice. Internally, right now, it's just performing each one at a time. So one optimization in the future that I'm working on is actually just combining that into one big parser function, right, that you just run. And that's going to give some efficiency gains. Thank you. Things like, so the question was, has this been proposed for things like migrations, for code bases, maybe things like libraries that change or functions that are deprecated? Absolutely. I think this is like a key application space, so refactoring and deprecating like outdated library calls. This is, again, tying into that idea of large-scale code modification. So really getting rid of a lot of these patterns. And so Google does this. They have really good internal tools for doing this and for doing it, for example, for C code specifically or Java. Here I'm identifying like a lot of opportunities maybe in languages that have less full-fledged support, and definitely that's one of the applications that it would be useful for. Yes, we are done. Thank you so much, everyone, for your time. Come talk to me.